Welcome. Now let's talk about numerical method runs in Matlab. So let's talk about the methods such as graphical method, second, oh, graphical method, incremental method, bisection method, Newton-Raphson method, regular fallacy method, and second method. Now let's talk about at first the graphical method. Graphical method is a visual technique used to estimate the location of the roots of a function. The idea is to plot the function over the interval and visually identify where the location crosses the 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 x-axis, where f of x equals to 0. Now, let's talk about the function run graphical method tab. Let's talk about it step by step. So x equals to length space x min x max 400. 400 generates evenly spaced points between x min and x max to evaluate the function on y equals to f of x. y equals to f of x evaluates the function at each point. Step 3. Plotting. Clears the axis with CLA. Plots the function in blue, adds a grid labels and horizontal dash line at y equals to 0. Step 4. Find diff sign y. Detects sign changes in y, which indicates where the function crosses the x-axis. Next is the interpolation, which is the step 5, which for each pair where a sign change occurs, linearly interpolates between points to estimate the x value of the root. Plots a green dot at the estimated root. Adds this root to table-friendly format. Step 6. Display. If new roots are found, notify the user. Otherwise, display all roots in a table. Now, let's proceed to incremental search method. Incremental search method, also called the incremental search method, finds a root by gradually stepping through the interval and looking for change in the sign of f of x. This indicates a root lies between two values. Now let's go to the code. Run incremental method tab. Let's talk about it step by step. Step 1. Unplotting. Clears the plot. Sets up a table to store results. X0 is the starting point. H is the incremental step size. Max ether is used to avoid infinite loops. Step 2. Loop logic. Steps forward from x0 by each iteration. At each step, evaluates the functions at 2 points x1 and x2. Step 3. Sign change detection. If f of x1 and f of x2 have opposite sign, a root lies in between. It estimates the root via linear interpolation or regular falsi style. Step 4. Result display. If root found, show iteration data. Else, notify that no root was found. Now, let's go to bisection method. Bisection method is a bracketing method given an interval a and b where f of a and f of b equal less than 0 repeatedly bisects the interval and chooses the subinterval where a sign change occurs. Now let's go to the code. Run bisection method tab. Let's talk about it step by step. Initialize, plot, and data table. Clear access, and prepare labels and title. Empty table for iteration result. Step 2. Initial check. Ensure function values at ends have opposite sign essential. Step 3. Iteration logic. Calculates midpoint C, evaluates f of C. Logs all values in table. Step 4. Convergence conditions. Stops if f of c is close enough to 0 or interval smaller than tool. Step 5. Interval update. Narrows down to half interval containing root. Step 6. Display results. Updates the table with the iteration values. Now let's go to regular falsi method or false position method. Like bisection, but instead of midpoint, regular falsi uses linear interpolation between endpoints to estimate the root. Now let's go to the Run regular falsi method tab. Let's talk about it step by step. Step 1. Initialization. Similar to bisection, plot grid levels. Step 2. Initial validity check. Needs opposite sign to ends like excuse me. Needs opposite signs at ends like bisection. Step 3. Regular falsi step. Uses the formula for linear interpolation. Much faster convergence for some functions than bisection. Now let's go to step 4. Sign-based interval update. Adjusts interval depending on the sign of FC. Step 5. Display iteration table. Output each step's variables. This regular falsi more accurate than bisection. Still a bracketing method. Granted convergence. It also can get stuck if one endpoint doesn't move. Now, let's go to Newton-Raphson method. Newton-Raphson method is an open root finding method that uses the first derivative of the function to iteratively converge to a root. It's very efficient and fast. If the initial guess is close to the actual root and the function is well behaved. The formula is xn plus 1 equals xn minus f of xn over f prime xn. Now let's go to the code. Newton Let's go to the code run Newton method tab. Let's talk about it step by step, how it works. Step 1, plot initialization. Clear the access, sets up the grid and labels. Starts iteration at user-defined initial guess, or the x0. Step 2, symbolic differentiation. Uses Matlab's symbolic toolbox to compute the derivative of f of x. Then converts converts it into function handle df of x that can be evaluated numerically. Step 3, evaluate function and derivative. F of x is f of xn and df of x is uh, uh, f of prime xn. Step 3, zero derivative check. If f prime f of xn equals to 0, the method can continue division by 0, so it stops. Newton update formula. Computes the next approximation xn plus 1. Logs all data, iteration number, current x0, f of x0, f prime x0, next guess x1. Step 6, convergence check. If the difference between x1 and x0 is below the tolerance, the root is considered found. Step 7, display result in table. Shows iteration history including function and derivative values. Now let's go to the last method, which is the second method. The second method is like Newton-Raphson but avoids computing derivatives. Instead, it approximates f prime x. Use two past function values. The formula is xn plus 1 equals xn minus f of xn multiplied by xn minus 1 over x f of xn minus f of xn minus 1. Now let's go to the code run second method tab. Let's talk about it step by step, how it works. Step 1, initialization starts with two initial guesses, x0 and x1. No need for derivative, good for complex functions. Step 2, division by 0 check. Prevents division by 0 if f of x1 minus f of x0 is equals to 0. Step 3, second update. Computes the next guess using the second line between the last 2 points. Logs all relevant data for table display. Step 4, convergence check. If change is within the tolerance, the root is found. Updates x0 and x1 for next iteration. Step 5, display table results. Each step includes previous guesses, function values, and new guesses. And that's my explanation for my Matlab code. Now let's run the